Somewhere above you, the sky is full of distance. Not just space distance, a quality so profound and so complete that no human experience quite prepares us for it. The distance between you and the ceiling of the room you rest in tonight is perhaps 3 meters. The distance between you and the top of the tallest building is perhaps a few hundred. Between you and the moon, a familiar, comforting presence in the night sky is roughly 380,000 kilometers. And the nearest star beyond our sun, just the nearest one, out of hundreds of billions in our galaxy alone, is approximately 40 trillion kilometers away. 40 trillion, a number that does not fit comfortably in the mind. A number that resists intuition. And yet that star, Proxima Centauri, a small and cool red dwarf, barely visible even through modest telescopes, is, by the standards of the cosmos, essentially our neighbor. Tonight, we explore one of the most profound and quietly beautiful mysteries of the universe. Not a mystery of violence or catastrophe, not a mystery that alarms or unsettles, but a mystery that, when you sit with it gently, opens into something like wonder. Why, if the universe contains trillions upon trillions of stars, is everything so extraordinarily, so incomprehensibly far apart? The answer is not simple. It is layered, like geological strata, each layer resting on the one below it, each one revealing something deeper about the nature of space, time, gravity, and the origin of everything. We have the whole night to explore it. There is no rush. There never was. As we begin our journey tonight, let us first simply sit with the distances, not to overwhelm, but to understand. Because before we can ask why everything is so far apart, we must first feel how far apart everything truly is. The distance from Earth to the Sun, approximately 150 million kilometers, is called one astronomical unit. Astronomers use it as a measuring stick for the inner solar system. It is a distance light covers in about 8 minutes. At that same speed of light, you would reach Mars in somewhere between 3 and 22 minutes, depending on where the two planets are in their orbits. You would reach Jupiter in about 43 minutes. Neptune, the outermost major planet, in roughly 4 hours. The outer boundary of our solar system, where the sun's gravitational influence fades into the broader galaxy, extends perhaps 1 to 2 light years from the Sunday. It takes light itself a year or two to reach the edge of our own solar neighborhood, and the nearest star beyond our sun is 4.2 light years away. To travel that distance in a spacecraft we could reasonably build today, perhaps reaching 1% of the speed of light, through some future advanced propulsion, would take over 400 years. Generations would be born and die on the journey. Civilizations would rise and fall back on Earth, and that is merely to reach the nearest star. The Milky Way spans 100,000 light-years. The nearest large galaxy is 2.5 million light-years away. The observable universe extends 46 billion light-years in every direction. The numbers increase so rapidly that they lose their power to impress. And so, instead of larger numbers, let us stay for a moment with one small fact. Between our sun and its nearest stellar neighbor, there is essentially nothing. A near-perfect vacuum, a handful of stray hydrogen atoms per cubic meter, cold, dark, and silent, stretching for 40 trillion kilometers. In that space between two neighboring stars, the most local of all cosmic distances, the emptiness is already almost absolute. Let us try, gently, to make this scale tangible through a simple thought experiment. Imagine the sun reduced to the size of a grapefruit, roughly 10 centimeters across, sitting on a table in front of you. On that same scale, Earth would be a grain of fine sand, roughly a millimeter across, orbiting at a distance of about 11 meters from the grapefruit sundae. You could hold Earth between your fingertips and barely feel it. Jupiter, the largest planet, would be a small marble, about a centimeter across, orbiting at roughly 56 meters from the sundae, still in the same room, perhaps. Neptune would be another small marble, orbiting at roughly 330 meters away, perhaps across a large field. The edge of our solar system, the outer Oort cloud, where comets are thought to reside in a vast, sparse shell, would be somewhere between 1,000 and 2,000 kilometers from our grapefruit sun on this scale. And the nearest star, Proxima Centauri, on this same scale where the Sun is a grapefruit on your table, would be another grapefruit, sitting approximately 2,800 kilometers away. 2,800 kilometers. On a scale where the entire solar system fits within a few kilometers, the nearest star is on the other side of a continent. And between your grapefruit and that distant grapefruit, there is almost nothing. An essentially perfect vacuum. No planets, no dust clouds, no warmth. Just the very thin gas of the interstellar medium, perhaps 1 atom per cubic centimeter in the more rarefied regions, drifting in a cold that approaches absolute zero. This is the texture of the universe. This is the fabric from which galaxies, for all their hundreds of billions of stars, are woven. Vast, mostly empty, and very, very quiet. As we continue, we arrive at the first and most fundamental answer to our question. The universe is far apart because it has been spreading apart since the very moment of its origin. Approximately 13.8 billion years ago, the universe began. Not in a particular place, not at a particular point in pre-existing space. Space itself, along with time, matter, and energy, came into existence, and from its very first moment, it expanded. This is important to hold carefully. The expansion of the universe is not the spreading of matter through pre-existing empty space, like an explosion scattering debris across a room. It is the expansion of space itself, the fabric of space-time growing, stretching in every direction simultaneously. Every point in space moving away from every other point, not because things are moving through space, but because the space between them is increasing. An analogy that is often used imperfect, like all analogies, but illuminating, is the surface of a balloon being inflated. Imagine dots drawn on the surface of an uninflated balloon. As the balloon expands, the dots move apart from one another, not because they are moving across the balloon's surface, but because the surface itself is growing. Every dot moves away from every other dot simultaneously. There is no center, there is no edge, there is only expansion. The universe works similarly, but in 3 dimensions rather than 2. In the very earliest moments of cosmic history, the universe was extraordinarily hot and extraordinarily dense. Matter and energy were compressed into a state we have no everyday analogy for. As space expanded, it cooled. And as it cooled, matter began to condense from energy. The first protons, the first atomic nuclei, eventually, the first complete atoms. The expansion has never stopped. In the 13.8 billion years since the universe began, space has stretched to a scale we can barely express. The distances between everything exist, in part, simply because of time. Because the universe has been expanding for almost 14 billion years. Consider this, and let it settle slowly, because it is one of the most remarkable things ever discovered about the cosmos. The universe is not merely expanding, it is expanding faster and faster. The rate of expansion is accelerating. This was discovered in the late 1990s by 2 independent teams of astronomers studying a particular kind of stellar explosion, a type Ia supernova, which can be used as a reliable cosmic distance marker. These supernovae always explode with approximately the same intrinsic brightness, which means that by measuring how bright they appear to us, we can calculate how far away they are. When the astronomers compared the distances and the recession speeds of these supernovae across cosmic history, they expected to find evidence that gravity was gradually slowing the expansion, pulling matter back together, decelerating the outward rush. This is what the models of that era predicted. What they found was the opposite. The most distant supernovae were fainter than expected. They were further away than they should have been if the expansion were decelerating. The universe was not slowing, it was speeding up. Something is causing the expansion of space to accelerate. Something that fills all of space, exerts a kind of negative pressure, and acts against gravity on the largest scales. Cosmologists call it dark energy, though the name is more a placeholder for our ignorance than a description of its nature. What dark energy is, at a fundamental level, remains one of the deepest unsolved mysteries in all of physics. It may be a property of empty space, itself a baseline energy that the vacuum possesses. It may be something more dynamic, changing over time. We do not yet know. What we do know is that it constitutes approximately 68% of the total energy content of the universe. And it means that the distances between galaxy clusters will continue to grow forever, as far as we can tell, at an ever-increasing rate. The universe is not merely far apart. It is becoming more far apart, faster and faster, with every passing moment. As we journey deeper into our question tonight, we arrive at what may be the most beautiful aspect of the answer, the realization that the universe's emptiness and the universe's structure are not opposites. They are partners. They are born together from the same process. In the very early universe, matter was distributed almost perfectly evenly throughout space. Almost, but not quite. There were tiny fluctuations in density, regions where matter was infinitesimally more concentrated than average, and regions where it was infinitesimally less so. These fluctuations were extraordinarily small, variations of roughly 1 part in 100,000, imperceptible, and yet they contained within them the seeds of everything. Gravity, patient, tireless, and cumulative, began to work on those tiny differences. The slightly denser regions exerted slightly more gravitational pull on surrounding matter. Matter drifted, slowly, toward those regions. As matter accumulated, those regions became denser still. Their gravitational pull increased. More matter followed. This process, gravitational collapse and structure formation, unfolded over hundreds of millions of years. Slowly, the near-uniform early universe developed texture, variations, concentrations. The regions that became denser lost matter to their surroundings. The regions that became less dense lost matter to their neighbors. And so, simultaneously, the universe developed both its densest structures, the filaments and clusters where galaxies reside, and its emptiest regions, the vast voids between those filaments. Every galaxy that formed made the surrounding space more empty. Every concentration of matter created a corresponding absence elsewhere. This is why the universe contains both the extraordinary richness of galaxies, with their hundreds of billions of stars, and the extraordinary emptiness of the voids between them. Both are the direct result of the same gravitational physics acting on the same initial fluctuations over billions of years. Structure and emptiness are two sides of the same cosmic coin. There is, woven through this story of structure formation, an invisible protagonist that deserves our full attention. Dark matter. We cannot see it. No telescope, optical, radio, infrared, or otherwise detects it directly, because dark matter does not interact with light or with any form of electromagnetic radiation. It passes through ordinary matter as though it barely exists. It has no electric charge. It emits no radiation. It absorbs none. And yet we know it is there. We know it from its gravitational effects. The stars, in the outer regions of spiral galaxies, orbit their galactic centers far faster than the visible mass of those galaxies can account for. Something unseen, something massive, must be providing additional gravitational force. Galaxy clusters contain far more gravitational mass than the visible galaxies within them suggest. The large-scale structure of the cosmic web, the specific pattern of filaments and voids, could not have assembled itself, as it did from ordinary matter alone. That unseen mass is dark matter, and it constitutes approximately 27% of the total energy matter content of the universe, compared to ordinary matter's mere 5%. For the story of why everything is so far apart, dark matter's role is foundational. In the early universe, before ordinary matter could respond to gravity, dark matter was already beginning to clump. Radiation pressure, the force of photons pushing outward, prevented ordinary matter from collapsing under gravity in the early, hot universe. But dark matter does not interact with radiation. It was immune to that pressure. It began forming gravitational structures, dark matter halos, while ordinary matter was still being held smooth by radiation. By the time the universe cooled enough for ordinary matter to move freely under gravity, the dark matter scaffolding was already in place. Ordinary matter fell into those pre-formed gravitational wells, and galaxies began to form. Without dark matter seeding those structures early, the universe might never have developed galaxies at all. The cosmic architecture we inhabit and the vast spaces between its features owes its existence to something we cannot directly observe. The universe is shaped, in large part, by something invisible. As we continue tonight, let us rise to the highest altitude of our perspective and look at the universe not as individual galaxies or even clusters, but as a whole, as a single, vast structure. When astronomers map the positions of galaxies across hundreds of millions of light years, something remarkable emerges. Galaxies are not randomly scattered through space. They are arranged in a pattern, a network of filaments, nodes, and voids that cosmologists call the cosmic web. The filaments are long, thread-like concentrations of galaxies and gas, stretching across hundreds of millions of light years. At the intersections of filaments sit the densest structures in the universe, galaxy clusters, containing anywhere from dozens to thousands of individual galaxies bound together by gravity. Between the filaments lie the voids, enormous, nearly empty regions of space. Some cosmic voids span hundreds of millions of light years. Within them, galaxies are rare or absent. They are the universe's blank spaces, its silences. The cosmic web is the large-scale texture of the universe, and it is, in its way, extraordinarily beautiful if you can see it at the right scale. Surveys of galaxy positions, rendered visually, produce images that look startlingly like neural networks, or the veins of a leaf, or the fine structure of a soap bubble foam, a pattern that seems almost deliberate, almost organic, emerging from the pure physics of gravity, acting on the initial conditions of the Big Bang. The voids are not empty of everything. They contain a thin scattering of galaxies, and they are filled with the intergalactic medium, a diffuse, extremely hot gas, invisible to optical telescopes, but detectable in ultraviolet and X-ray light. Even in the cosmic voids, the universe is not absolutely empty. But compared to the filaments and clusters, the voids are as close to nothing as the universe gets. They are the spaces that make the structure visible, the silence that makes the music audible. Deep within the cosmic web lie structures of emptiness so vast they have earned a name of their own supervoids. A supervoid is a region of the universe substantially underdense compared to the cosmic average, a vast, nearly empty bubble in the fabric of the cosmos. The largest known supervoids span hundreds of millions to over 1 billion light-years across. The most famous of these is the Boötes void, a roughly spherical region of space, approximately 330 million light-years in diameter, located in the direction of the constellation Boötes. Within this enormous volume, the density of galaxies is dramatically lower than average. What should contain, by extrapolation from the surrounding universe, perhaps 2,000 galaxies, contains only a handful, 330 million light-years across, mostly empty. To put that in perspective, if the Milky Way were located at the center of the Boötes void, astronomers on our world in the early 20th century, before the existence of other galaxies was even confirmed, would have seen nothing but darkness in every direction for hundreds of millions of light-years. The nearest galaxies would have been so distant as to be invisible to the telescopes of that era. The existence of structures like the Boötes void raises interesting questions for cosmologists. Is such a void consistent with our models of structure formation? Or does it represent something unexpected? Current understanding suggests that such voids, while large, are not entirely inconsistent with the predictions of the standard cosmological model, though they push at the boundaries of what the models comfortably predict. The universe's emptiness, it turns out, is not uniformly distributed. Just as the universe's matter clusters into filaments and clusters, the universe's emptiness clusters into voids, regions where the absence of matter has become, in its own way, a defining feature of the landscape. Emptiness, like matter, has structure. As we shift our attention now from the spaces between galaxies to the spaces within them, a natural question arises. With hundreds of billions of stars in a galaxy like the Milky Way, why don't they collide? The answer lies in geometry, in the relationship between the size of stars and the distances between them. Our Sun is approximately 1.4 million kilometers in diameter. That sounds large, and by human standards, it is almost incomprehensibly so. But the distance to the nearest star is approximately 40 trillion kilometers. The ratio of stellar size to stellar separation is roughly 1 to 28 million. Imagine once more our grapefruit scale model. The Sun is a grapefruit, the nearest star is another grapefruit, and between them lies 2,800 kilometers of empty space. The probability of those two grapefruits colliding if they were scattered randomly through a region of space on that scale is extraordinarily small. Now extend that logic to an entire galaxy. The Milky Way contains somewhere between 100 and 400 billion stars. They are distributed through a disk roughly 100,000 light-years across. On our grapefruit scale, the entire Milky Way would span something like several hundred million kilometers, roughly the distance from Earth to Mars. Within that Mars orbit-sized disk, there are 400 billion grapefruits, widely spaced, rarely encountering one another. When two galaxies merge, a dramatic event that unfolds over hundreds of millions of years, the individual stars pass through each other's distribution like two clouds of smoke interpenetrating. Gravity distorts their orbits. Gas clouds collide. New stars burst into existence in the shock of galactic collision. But the individual stars, those hundreds of billions of individual grapefruits, almost never physically collide. The galaxy is not crowded. It is a vast space in which solitude, not collision, is the natural state. Let us now turn our attention to what actually inhabits the spaces between stars within a galaxy, because even within a galaxy, the spaces between stars are not entirely empty. The interstellar medium is the collective name for the matter that exists between stars, the gas, dust, and charged particles distributed throughout the galaxy. It is extraordinarily diffuse by any earthly standard. In the densest molecular clouds, the regions of the interstellar medium, cold and dense enough for molecules to form and stars to be born, the density reaches perhaps 1 million molecules per cubic centimeter. That sounds like a lot, but 1 million molecules per cubic centimeter is still a better vacuum than the best laboratory vacuum achievable on Earth. The interstellar medium is, by any practical measure, extremely thin, and yet it is enormously consequential. The interstellar medium is the raw material of star formation. When regions of a molecular cloud become dense enough, either through gradual accumulation or triggered by a passing shockwave from a nearby supernova, gravity can overcome the gas pressure and the cloud begins to collapse. Over millions of years, that collapse produces new stars, potentially surrounded by planets. The interstellar medium also carries the chemical legacy of previous stellar generations. When a star dies, either in a quiet shedding of its outer layers as it becomes a planetary nebula, or in the violent explosion of a supernova, it scatters its material back into the interstellar medium. That material is enriched with the heavy elements forged in the star's core: carbon, oxygen, nitrogen, silicon, iron. The next generation of stars forms from this enriched material, and the planets around those stars inherit its chemistry. Your body contains atoms that cycled through at least one, and probably several, previous stellar generations before being incorporated into the solar nebula from which our sun and planets formed. The space between stars is not merely empty. It is a chemical reservoir, a library of stellar history. As we continue our journey, we arrive at one of the most quietly profound ideas in all of astronomy: the realization that in looking at the distant universe, we are not merely looking across space. We are looking back through time. Light travels at approximately 300,000 kilometers per second. It is the fastest speed at which information can travel, a fundamental limit woven into the structure of space-time itself. At that speed, light from the sun takes approximately 8 minutes to reach Earth. From the nearest star, 4 years. From the center of the Milky Way, about 26,000 years. From the Andromeda Galaxy, 2.5 million years. When you look at the night sky, every star you see is a time capsule. The light entering your eyes left its source years, decades, centuries, or millennia ago. You are seeing those stars, not as they are, but as they were. The star, Betelgeuse, one of the brightest stars in the constellation Orion, is approximately 700 light-years away. The light you see from Betelgeuse tonight left that star 700 years ago when the Black Death was sweeping across medieval Europe. Whatever Betelgeuse looks like right now, in this present moment, you will not know for another 700 years. For distant galaxies, this effect becomes extraordinary in its implications. The Andromeda Galaxy, visible to the naked eye, is seen as it was 2.5 million years ago before our species existed. The most distant galaxies observed by the James Webb Space Telescope are being seen as they appeared over 13 billion years ago when the universe was in its infancy. The vast distances of the universe mean that every observation is an archaeological act. We are sifting through the light of the past, piecing together the history of the cosmos from the fossils of ancient photons. The universe does not show us itself as it is. It shows us its history. Its distances are its memory. Consider this. The finite speed of light imposes something even more profound than a time delay on our observations. It imposes a fundamental limit on what we can ever observe. The universe is approximately 13.8 billion years old. Light has been traveling since its earliest moments. The maximum distance light could have traveled from any given point in that time, accounting for the expansion of space, defines a sphere around us called the observable universe. That sphere extends approximately 46 billion light-years in every direction. The discrepancy between the age of the universe, 13.8 billion years, and the radius of the observable universe, 46 billion light-years, arises because space itself has been expanding as the light traveled, carrying the sources of that light further away. Beyond the edge of the observable universe, space almost certainly continues. The universe is likely far larger than what we can observe, possibly infinite. But no light from beyond that horizon has had time to reach us. We cannot observe it. We have no access to it through any form of electromagnetic signal. What this means for the question of cosmic distances is both humbling and strangely comforting. The universe we know, the 2 trillion galaxies within the observable sphere, is already so vast as to be practically inexhaustible, and yet it may be a tiny fraction of the whole. There is a further consequence. As dark energy accelerates the expansion, more and more of the universe recedes beyond our observable horizon. Distant galaxies, already receding, will eventually be moving away from us faster than light can travel between us. When that happens, they pass beyond our horizon, not destroyed, not gone, but permanently inaccessible, as unreachable as if they had never existed from our perspective. In the very distant future, tens of billions of years from now, the observable universe will contain only our own local group of galaxies, as everything else recedes into permanent darkness. Future astronomers, if any exist, might look out at a much smaller, much lonelier sky. We are fortunate to exist now, when the universe is still young enough and close enough to be seen in its fullness. As we continue our gentle exploration, let us turn to a realization that carries particular wonder, the possibility that the distances we have been contemplating are not merely a feature of the universe, but a condition for our existence within it. If stars were much closer together, if the average separation in the Milky Way were a fraction of a light year rather than several light years, the consequences for planets and life would be significant. Closer stellar spacing would mean more frequent gravitational encounters. Stars passing relatively near one another would perturb the orbits of the planets around each star. The long-term orbital stability that Earth has enjoyed, the billions of years of consistent climate conditions that may have been necessary for complex life to evolve, would be disrupted. Planets might be flung into new orbits. Solar systems would be less predictable, less safe. Additionally, more closely packed stars would mean a higher rate of supernovae in any given volume of space, and therefore higher fluxes of high-energy radiation. A supernova occurring within a few dozen light-years of a planet could strip away its ozone layer and expose its surface to lethal ultraviolet radiation. Life, if it had established itself, might be repeatedly set back or extinguished. In the dense, star-packed central regions of galaxies, where stellar separations are much smaller than in the outer disk, astronomers have noted that these hazards increase. The galactic habitable zone, the ring of the galactic disk, where conditions for life-bearing planets are thought to be most favorable, is the region far enough from the dense center to avoid these hazards, but not so far out that stellar populations are too sparse and chemically unenriched. Our solar system sits within this zone, in the relative quiet of the outer disk, at a comfortable distance from our stellar neighbors. The emptiness between stars is not merely a geometric fact. It may be one of the reasons we are here to observe it. Deep within the question of cosmic distances lies one of the most evocative, unsolved mysteries in all of science. The question of whether other minds exist in that vast emptiness, and why, if they do, we have not yet heard from them. The Milky Way contains between 100 and 400 billion stars. Around many of those stars orbit planets. Astronomers using data from the Kepler Space Telescope and other observatories have estimated that the Milky Way may contain billions of potentially habitable planets, rocky worlds, orbiting their stars at distances where liquid water could exist on their surfaces. Life as we know it requires liquid water. Chemistry requires atoms forged in stars. Time requires gravitational stability. All of these things exist in abundance in our galaxy. And yet, we have searched the sky across radio waves, visible light, and other wavelengths for signals that might indicate the existence of technological civilizations elsewhere. And thus far, we have found nothing that can be convincingly attributed to extraterrestrial intelligence. This is the Fermi paradox, named for the physicist Enrico Fermi, who reportedly asked, given the vast number of stars and the presumed prevalence of life-supporting conditions, where is everyone? The distances we have explored tonight are part of the answer, or at least part of the context. Even if the galaxy teems with civilizations, the distances between them are so vast that signals take thousands to millions of years to cross the gulf. A civilization broadcasting from a star 1,000 light-years away is sending us a message we will receive in 1,000 years, and to which we could not reply, and receive an answer for another 1,000. The emptiness is not evidence against life elsewhere. It is simply a measure of how isolated any civilization must be, how each island of consciousness in the cosmic ocean exists, at least on any humanly meaningful timescale, essentially alone. That is not a comforting thought, but it is an honest one, and in its honesty, it adds something to the weight and the wonder of our own existence here, on this particular small island, in this particular quiet corner of the Milky Way. As we move through the quieter hours of our exploration, let us trace the story of cosmic structure all the way back to its deepest roots, to a time so early and a scale so small that the physics involved belongs to quantum mechanics rather than cosmology. The near-perfect uniformity of the early universe and its tiny imperfections has an origin that may seem surprising. Those small fluctuations in density that became the seeds of all large-scale structure are thought to have originated as quantum fluctuations in the very earliest moments of the universe's existence. Quantum mechanics, the physics of the very small, tells us that nothing can be perfectly still. At the quantum scale, there is an irreducible uncertainty, a fundamental jitteriness built into the fabric of reality. The position and momentum of a particle cannot both be precisely known simultaneously. The energy of a vacuum fluctuates constantly, producing and annihilating pairs of virtual particles. In the early universe, during a period cosmologists believe was characterized by extraordinarily rapid expansion, called cosmic inflation, these quantum fluctuations in the density of the infant cosmos were stretched from subatomic scales to cosmic scales. Variations that existed at the quantum level, smaller than the nucleus of an atom, were inflated to scales that would eventually become the seeds of galaxy clusters. The universe's large-scale structure, the filaments, the voids, the galaxies themselves, traces back through an unbroken chain of physical causation to quantum uncertainty in the universe's first moments. The emptiness between galaxies, those vast supervoids spanning hundreds of millions of light-years, has its ultimate origin in the random quantum fluctuations of a newborn universe smaller than an atom. There is something deeply moving about this chain of causation. The physics of the very small and the physics of the very large are not separate domains. They are chapters of the same story. And the universe, in its totality, is the consequence of that story playing out over 13.8 billion years. Let us rest with one final, quiet idea about the nature of the emptiness we have been exploring, an idea that is both strange and strangely comforting. Empty space is not nothing. This is not merely philosophical. It is a result of quantum mechanics, and it has measurable, observable consequences. The quantum vacuum, the lowest possible energy state of empty space, is not a passive, featureless void. It is filled with what physicists call zero-point energy, a baseline level of energy that cannot be removed, that the vacuum always possesses, regardless of how thoroughly all matter and radiation have been evacuated. From this vacuum energy arise what are called virtual particles, pairs of particles and antiparticles that briefly flicker into existence, borrowing energy from the vacuum, and then annihilate back into nothing. This is not a hypothetical process. Its effects can be measured. The Casimir effect, a measurable attractive force between two very closely spaced metal plates in a near-perfect vacuum, arises directly from vacuum fluctuations. The plates exclude certain wavelengths of vacuum fluctuations from the space between them, creating an energy imbalance that produces a measurable force. Empty space, at its deepest level, is alive with subtle, ceaseless activity. And there is one more layer to this. The dark energy that is causing the expansion of the universe to accelerate that mysterious constituent that makes up 68% of the universe's energy budget may be related to the energy of the quantum vacuum. Whether dark energy is the vacuum energy or something more dynamic and complex is one of the central questions at the frontier of theoretical physics. The emptiness of space may be, in a profound sense, the most energetic thing in the universe. What appears to be nothing is, at its foundation, everything. As we approach the final chapters of our journey tonight, let us consider what the future holds for the vast distances we have been exploring, because those distances are not fixed, they are growing. And they will continue to grow in ways that have a particular kind of melancholy beauty. Right now, we live in a cosmological epoch that is, in certain respects, extraordinarily favorable for observation. Thousands of galaxies are close enough to be studied in detail. The cosmic web is visible to us in its broad architecture. We can observe the universe all the way back to its earliest chapters. But the expansion of space driven by dark energy is carrying distant galaxies away from us with increasing speed. There is a threshold already crossed for galaxies beyond a certain distance, beyond which the space between us and a galaxy is growing faster than light can travel through it. Galaxies beyond this threshold are already, in a practical sense, forever unreachable. Their light is still traveling toward us, because it has been traveling for billions of years. But new light they emit today will never reach us. Over the billions of years to come, more and more galaxies will cross this threshold. The Virgo cluster, the nearest large galaxy cluster beyond our local group, will eventually recede beyond the reach of any signal we could send. Then, further clusters. Then, on timescales of tens to hundreds of billions of years, even the nearest galaxies beyond our local group will be beyond practical reach. The Milky Way will eventually merge with Andromeda, and possibly with a few other members of our local group, into a single, large, elliptical galaxy. And that merged galaxy will be, on the timescales of dark energy's work, increasingly alone, surrounded by an expanding darkness, in which all other galaxies have receded beyond the visible horizon. Astronomers billions of years from now, if any exist, will look out at a sky containing perhaps only a few dozen visible galaxies, all members of their own merged local group. The cosmic web, the galaxy clusters, the great filaments, all of it will have receded into permanent, unreachable darkness. They may not even know those structures ever existed. We are seeing the universe at its most legible, and that too is something to hold with gratitude tonight. Let us pause, in the quiet of the later hours, and ask a question that sits at the boundary between physics and philosophy. What do the vast distances of the universe tell us about the nature of reality itself? The universe did not have to be this way. The constants of nature, the strength of gravity, the speed of light, the rate of expansion could, in principle, have taken different values. A universe with stronger gravity might have recollapsed long before galaxies formed. A universe with weaker gravity might have expanded so rapidly that matter never had time to concentrate into stars and galaxies. The universe we inhabit is one in which the constants of nature are balanced, not perfectly tuned for life, but within a range that permits the formation of complex structures, long-lived stars, stable planetary systems, and ultimately chemistry rich enough to support biology. The vast distances of the universe are a consequence of those constants. The speed of light, the strength of gravity, the energy density of dark energy, all of these combine to produce a universe of this particular scale, this particular texture, these particular separations between things. Whether this arrangement is the result of chance, of some deeper physical principle, or of something else entirely, this is a question that physics alone cannot yet answer. It sits at the very frontier of inquiry, in the company of questions about the nature of dark matter and dark energy, the origin of the universe's initial conditions, and whether our universe is one of many. What we can say is this: the universe is the way it is. It has produced, within its vast and mostly empty architecture, the conditions for stars, planets, chemistry, biology, and minds capable of asking these questions. The distances are not an obstacle to existence. They are part of the fabric within which existence has become possible. As we move gently toward our conclusion tonight, let us consider the emotional and philosophical dimension of everything we have explored. For many people, the vast emptiness of space is experienced as something cold, something isolating. The scale of the universe, the hundreds of billions of light years, the trillions of stars separated by unimaginable distances can feel, when contemplated in a certain frame of mind, like a kind of indifference. A universe that does not know we exist. A universe too large to care. But there is another way to hold this. The emptiness of space is not an absence of something that should be there. It is a structural feature of a universe that works. The vast distances between stars protect planetary systems from the gravitational disruptions that would make long-term stability impossible. The expansion of space has been carrying matter apart since the Big Bang, and in doing so, it allowed matter to cool, to condense, to form the structures from which everything we know emerged. The void is not empty of meaning. It is full of context. Consider what the emptiness has done for us. 4.5 billion years of relative isolation in the outer disk of a quiet spiral galaxy. No catastrophic stellar encounters. No nearby supernovae devastating the biosphere. A star that burns steadily, without violent outbursts, on a timescale that allowed life to evolve, from single cells to everything that has ever lived. The emptiness held us, gave us time, protected the long, slow process of biological evolution from disruption. In a denser, more crowded region of the galaxy, the history of this planet might have been very different, or there might be no history here at all. The distance between stars is not cold indifference. It may be, in its way, a kind of shelter. Consider this. As we near the end of our journey, one of the most persistent misconceptions about cosmic scale. Many people feel, when confronted with the vastness of the universe, that it diminishes them, that the incomprehensible distances between stars and galaxies render human life, human experience, human consciousness somehow insignificant, trivial, a statistical irrelevance in an indifferent cosmos. But insignificance and smallness are not the same thing. A grain of sand is small. But the information encoded in the atoms of that grain of sand, the quantum states of trillions of electrons and protons, exceeds the information content of the most complex human library. Smallness of scale does not imply simplicity of nature. And you are not a grain of sand. You are a biological organism of extraordinary complexity. Approximately 37 trillion cells, each containing a nucleus holding roughly 2 meters of DNA, encoding approximately 20,000 genes. A nervous system processing billions of signals per second. A brain generating conscious experience, subjective awareness, the very phenomenon that remains, arguably, the deepest unsolved mystery in all of science. The universe, across its 2 trillion galaxies and 10 to the power of 24 stars, as far as we know, has produced this complexity exactly here. On this planet, perhaps on others as well, we do not know. The universe did not intend to produce you. Physics is not purposeful in that sense. But the physics that produced the vast emptiness between galaxies also produced the stable star, the rocky planet, the liquid water, the organic chemistry, and the 4 billion years of biological evolution that resulted in a mind capable of comprehending the distance between galaxies. The scale of the universe does not diminish you. In context, it makes you more extraordinary. And so we arrive, gently and without hurry, at the end of our journey tonight. We have traveled far together, from the 40 trillion kilometers separating our sun from its nearest stellar neighbor, through the architecture of the cosmic web, those vast filaments and supervoids that structure the observable universe on scales of hundreds of millions of light years, through dark matter's invisible scaffolding and dark energy's quiet, relentless work of expansion, through the quantum origins of cosmic structure and the finite speed of light that makes all distance a form of time. We asked a simple question: why? If the universe contains trillions of stars, is everything so far apart? And we found that the answer is woven into the very nature of the universe. The universe is far apart because it has been expanding since its first moment, because space itself has been stretching for nearly 14 billion years, carrying everything within it on a long, patient, outward journey. It is far apart because gravity, patient, cumulative, working on quantum scale fluctuations, drew matter into concentrated islands, while leaving the vast regions between those islands emptier than before. It is far apart because dark energy, mysterious in its nature, immense in its effect, is accelerating that expansion, ensuring the distances will only grow. And it is far apart, perhaps most importantly, because a universe built differently, one with different constants, different rates, different scales, might not have been a universe where stars burn steadily for billions of years, where planetary systems remain stable across geological time, where chemistry has the time and space to organize itself into something that breathes and wonders. The emptiness is not incidental, it is architectural. It is part of what makes existence here, this particular warm, complex, unlikely existence possible. Tonight, in whatever small, sheltered space you have chosen for rest, the universe extends in every direction. The nearest star is 40 trillion kilometers away. The nearest large galaxy is 2.5 million light years. The edge of the observable universe is 46 billion light years in every direction. And between you and all of that distance, there is warmth, there is air, there is the soft weight of a body at rest, the quiet rhythm of breathing, the darkness behind closed eyes. You are, by every cosmic measure, extraordinarily small, and you exist in a space, this planet, this atmosphere, this brief window of biological time that has been sheltered by the very emptiness surrounding it, protected by the distances we have been contemplating. The universe did not make you. Physics made you, the same physics that made the stars and the voids and the dark matter filaments and the quantum vacuum. The same laws that hold galaxy clusters together held the atoms of your body together across billions of years of stellar and planetary and biological history until they arrived at this moment, this breath, this rest. There is nothing alarming in the vastness. There is only context. You are matter that became conscious, a small region of the universe that has, through an extraordinarily long and intricate series of physical events, become aware of itself, capable of asking where it came from, capable of understanding, at least partially, the answer. The distances between the stars are ancient. The expansion of space has been ongoing since before the sun existed. The cosmic web has been assembling itself across billions of years. And you are here, at the end of all that becoming, resting in the quiet center of your own small world. That is enough. That is, in fact, everything. Thank you for exploring with us tonight. May your rest be as deep as the space between the galaxies, vast and quiet and unhurried and full of something that, in the silence, feels almost like peace.